In this problem, we find derivatives, a couple of derivatives of a function. Billy's been doing some calculus, and besides the derivative values, he's given us some information about a function. He found no horizontal asymptotes. He did find a vertical asymptote at x equal 1, and only one intercept. That's at the origin, 0, 0. So it's kind of important to notice later on. We never cross the x-axis or y-axis anywhere other than this one point. All right. The derivatives of the functions are given, and we're asked to find sign distributions for the two derivatives and then graph the function. All right. I don't have a lot of space here, so I'm going to do this in a couple of steps. But what you want to put on each of these number lines is the places where the derivatives are equal to 0, or where they do not exist. In this first derivative, I would factor that numerator so that I can see the zeros easier. I see that an x will factor out, and I can quickly from this see that it's going to be 0 at x equals 0 and at x equal 2. And I can also see that it does not exist at x equal 1. And that's to be expected. There was a vertical asymptote according to Billy at x equal 1, so we shouldn't have a slope there on our first derivative. So these are the three partition values. These are the places where something exciting is going on the graph. So we'll place those on our number line, and we'll keep track of what's going on at those. At 0 and 2 we have a 0 derivative, so horizontal tangent line, and then I'll just stack a dne over the 1, which by the way must carry forward, so there must be a dne on my second derivative as well at that point. We'll look at that in a moment. But now I can check the signs in each of these intervals and check to see whether the derivative is positive or negative, which will tell me where the function's increasing or decreasing. And that'll be important when I get to the graphing of the function piece of this. Walking down the line here now, I'm going to view the top as a product of these two numbers, and notice the denominator, since it's squared, is always going to be positive. So if I view this as a product divided by something squared, that something in the denominator is always going to be positive. It's only going to be the numerator subtract a number between 1 and 2. If I subtract 2 from it, I end up with negative. So I have positive for the x value and negative for the x minus 2 value. That means a negative in here. The function must be decreasing. So there must be a local minimum at x equal 2. And if I step over between 0 and 1, the x value again is still positive, but the x minus 2 value is also, I guess, still negative, same value, same result as before. So in here we're seeing decreasing. So this vertical asymptote is decreasing on both sides. That helps me visualize what the graph must look like there, and when we get to the graphing stage we'll put that on. And then let's look at this last interval here. On the left side of 0, the x value is going to be a negative value, and the x minus 2 is also going to be a negative value. So the product will be positive. So in this region my function must be increasing, which means I must have a local maximum at x equals 0. It's increasing and then decreasing. Right? The analysis of the second derivative goes the same way. You're interested in knowing when is this equal to 0 and when does it not exist. There's nothing to factor up here, but this is never 0, and this does not exist at x equal 1. So x equal 1 is the only thing to partition the second derivative sign distribution number line with. So now we just check the signs on both sides. And if I look at the signs of the numerator and denominator on each of these intervals, I can tell where the function is concave up and concave down. Numerator is at 2, so that's positive on both sides. The x minus 1 cubed, if x is larger than 1 and I subtract 1, it's going to be positive, and a positive cubed is positive. So out in here we should see the function being some shape like this. It's going to be concave up. Alright, on the left side of 1, the numerator will be negative now, and a negative cubed is negative. So in here we're going to see concave down, so some part of that shape. Alright, now I'm going to make myself some more room here. And we can start thinking about the graph paper now. So if I draw a set of axes here, again, some of the key values to place on here that Billy found is that the graph goes through the origin right here. It has a vertical asymptote at x equal 1, and the other value that we found of interest is over here at x equal 2. And I'd really like to plot a point that goes along with this, but I don't have the function. This is a local minimum, and notice the function's decreasing and then increasing as we pass through 2. So the function must be up in here someplace. If it dropped down and touched, or dropped down below and came back up, then there would have to be other x-intercepts, and Billy found only the 1. So the y value at x value 2 must be some positive number. I don't know which one, but I'm allowed to just pick a reasonable value here, so I'm going to place that right there. If I now think about what's going on in each interval, kind of slice this number line into pieces at any interesting value here, then start connecting the dots. Out in this region, I need to be 0 tangent line on the end and increasing concave up, so it must be this shape. That means the graph must look something like this out here. In between 1 and 2, I need to be decreasing concave up. I've got a vertical asymptote on this side and a horizontal tangent line at this side. So this one must be going off to infinity that way and connecting up with this one on this side. And I want a nice smooth transition, no wiggles in there. There are no other inflection points. In between 0 and 1, I want to be decreasing concave down. I've got a horizontal tangent line at this side and decreasing towards a vertical asymptote on that side. So on this, from this